Hello, my name is Eric Hand. This past summer, I worked on a structural health monitoring for composite panels project in the Aerospace Engineering Department at the University of Michigan under the mentorship of Professor Susnick. Structural health monitoring provides a non-invasive way of checking the integrity of structures. It works by using actuators to send guided waves through the structures and then monitoring the response of the waves. The responses of the waves will then hopefully give an indication of where damage is in the structure and how severe the damage is. Piezoceramic transducers, or PZTs, are used as both the actuators and sensors in this project and are bonded to the structure of interest. PZTs in a wide variety of shapes and sizes are shown here. When an electric field is applied to a PZT, a mechanical strain is produced. This is called the piezoelectric effect. This effect allows us to use the PZTs as actuators by giving it an alternating electric field. This will cause a mechanical strain in the PZT, and the waves will be sent through the structure to which it is attached. The piezoelectric effect works backwards as well. When a PZT is strained, an electric charge is produced in the PZT. This effect allows us to use the PZTs as sensors. When the waves in the structure mechanically strain the PZT, the associated electric field that is produced can be monitored. This is the panel the majority of my testing was conducted on. The panel consists of a woven composite base sheet of foam core and stiffeners. At the center is a specially designed piezoceramic transducer called a Clover transducer, which is arranged in a circular alignment that allows for a wider range of the structure to be tested when used as an actuator. The Clover transducer is divided up into 8 different wedge-shaped segments, and each can act as an actuator or sensor. At the outside of the structure, more PZTs are attached. The illustration on the left shows an example experiment performed on the panel. In this setup, the input signal is applied to PZT4, denoted as P4 and highlighted in red. The input signal comes from a function generator and was passed through an amplifier. The resulting guided waves are then monitored by sector 7 of the Clover transducer, denoted with a 7 and highlighted in green. The response from sector 7 is monitored with the help of an oscilloscope. This setup will be done with the panel in an undamaged state and will be tested over a wide range of input frequencies. Then, simulated damage in the form of a concentrated mass will be placed on the panel. The illustration on the right shows an example of where on the panel damage would be placed. With the simulated damage in place, the experiment will be performed again. Comparing the signal received from the sensor when the panel was in an undamaged state with the signal received from the sensor when the damage was placed on the panel can inform one whether or not the damage was detected. Various different actuator and sensor combinations, along with different damage locations, will be possible for testing on this panel. The data from the oscilloscope will then be collected and transferred to MATLAB in order to analyze it. This is an example of some of the results from an experiment. In this test, the actuator was sector 7 of the Clover transducer and the sensor was PZT4. This was tested at an input frequency of 20 kHz. The blue curve represents the response from the sensor when the panel was in an undamaged state. The red curve represents the response from the sensor when simulated damage was placed in the same location on the panel as was shown on the previous slide. As can be seen, there is a difference in the two response signals. This suggests that the damage was detected by the sensor. Many plots similar to this were made over the course of the summer to try and detect which actuator and sensor combinations were more sensitive to detecting damage, and which input frequencies yielded better results. Thank you for watching my video. I hope this brief introduction to structural health monitoring was as intriguing as I found the work to be.